Get started. First of all, good morning, good afternoon, good evening, depending on your time zone. Thank you all for joining us here. I'm David Cantor, as many of you know, one of the founders of MLCommons, head of MLPerf, and it is my pleasure to welcome you all to the Training 6.0 press briefing. I'm joined by Alejandro, our program manager for this effort, Shreya and Pavan, who are working group co-chairs, as well as Paul, who is our outgoing working group chair, and then all of our submitters. So next slide. This is the standard housekeeping slide. This briefing is recorded and will be posted to a Google Drive that contains a lot of the critical documents for this round of MLPerf training. That includes the results, the supplementals that all of our submitters have filled out to help explain and elaborate upon their submission, the press release, and then the team has done a really fabulous job of putting together technical blog posts explaining our new benchmark. So hopefully that'll be really helpful to you as you are working on your stories and analysis. Next slide, please. This is an agenda for the briefing. We're going to try to get through my section as quickly as possible so we can get on to the more exciting technical stuff and what our submitters have done as well, and then the Q&A. So I hope when we get to the Q&A, everyone will have lots of questions. Next slide, please. Just as a reminder about who we are, MLCommons is a nonprofit. We're an industry consortium, over 125 members. You can see the logos up here. And, the project that got us all started was, of course, MLPerf, which is the benchmark of choice for AI system performance and efficiency. And on one side of this slide here, you can see just some of the ways that our members use MLPerf to talk about their products, whether they are systems, whether they are cloud instances, whether they're silicon. But MLPerf is used in a number of different ways, including bringing up new systems, characterizing them well above and beyond just the submission process. But everything we do here is for the community to win together, and these are just some of those examples. Next slide, please. One of the things that I've always said is very beautiful about machine learning and AI is the demand for AI is so vast that we get to pull on every lever at our disposal to improve performance. This is what makes MLPerf such a fascinating, challenging, and interesting benchmark, is it is a full stack benchmark. It is not just about silicon, but it is about silicon. It includes things like software, the scale of submission, how you even sort data, algorithms you're using, the networking, everything comes together to deliver the performance that people demand to train the next generation of AI models that are going to unlock new capabilities, as well as for inference. And so as a benchmark, MLPerf gets to measure all of these advances rolled together, which both makes it, an incredibly powerful tool. You can compare different generations of your software using MLPerf. You can compare different generations of accelerators or even network upgrades. So, and there's just a tremendous amount to be gleaned. Next slide. One of the key things I want to emphasize to folks is when we set out with MLPerf, I think there's really four key values that we captured that really made MLPerf successful, which is the relevance. And we're going to be talking a lot about that today in terms of upgrading and changing to newer, more representative workloads. We need to be fair and neutral. There's a lot of effort that's gone into writing down our rules, into the peer review process, into making sure that everyone can compete on as fair of a level playing field as possible. And that helps to drive the inclusion. We want as much participation as possible, so the benchmark is broadly useful to the entire community, from buyers to sellers to researchers. And we want it to be reproducible, right? This harkens back to one of the core principles of the scientific revolution. Part of the joy of MLPerf is we get to measure performance and then see how it improves over time and start helping guide the industry in the right direction to make AI more capable and more efficient. And so those are some of the key things that we always want to capture with any benchmark. And I think that's part of what helped us capture lightning in a bottle with MLPerf. Next slide. MLPerf is broadly used for purchasing, and this is one of the slides that I'm just tremendously proud of. The quote here is from our friends at the National Lab of the Rockies. This is a U.S. government lab that does a lot of advanced research, and I think the quote says it all. It's not about what benchmark to use, it's about which test within MLPerf were they going to use. And ultimately, it was a great experience for them. That's just one of many examples of how buyers are using MLPerf and how we bring the community of folks who are using and deploying AI together with the folks who are developing it. We see broad spread adoption, lots of use in RFPs, and then increasingly, we're seeing more and more partnerships with different organizations to get access to data sets, to get access to models, and even working with some of the official standards bodies like ISO SC42. And all of these are a testament to the work of our community, bringing everyone together, and the fact that those four principles behind MLPerf, I think, really resonate with the broader industry. And help us both be the barometer of progress and help drive that progress with our members. Next slide, please. All right, so now I get to turn it over to Shreya, who is one of our fabulous co-chairs for MLPerf training, and she gets to dive into a bit more of the details. So Shreya, please take it away.
Hey, thanks, David, for the introduction. Hi, everybody. Laurie, can we please go to the next slide? Right. So today I'm going to talk about the MLPerf training benchmark. We are the two chairs, Pawan and I. Paul too was our chair before. So I'll talk a little bit about MLPerf training itself, and then I will dive into our results from 6.0. Next slide. So the performance benchmark, the way we measure MLPerf training is using time to train. What time to train essentially means is how fast a system can train a model to a target quality metric. So this is different from raw throughput because we also account for convergence efficiency. Next slide. So the other metric we have is power. And power measures the average power consumed by all the compute nodes and the interconnect network during the timed workload. So both the performance and power are two of our training metrics for MLPerf training. And the MLPerf advantage is that we measure the full system, hardware and the software impact of the configuration choices. So this ensures that our performance reflects the real world time to solution rather than just the peak theoretical speed. Next slide. So the way that we've built our benchmark is that we do proxy modeling. Essentially, if you look at the results, you might see, for example, that the DeepSeek V3 best performance score was about 2 minutes. That doesn't mean that we trained this super large 600 billion parameter model in 2 minutes. But what it actually means is that in the MLPerf training slice, which is just from wherever we're starting the training to the quality metric that we have set up for the benchmark, it takes about 2 minutes to train to there. Next. So this is what that slice looks like. On the x-axis, we have the training tokens, and the y-axis, we have the loss. So if you try to train this model end-to-end on, say, like billions or trillions of tokens, it's going to take a really long time to train. But that's really hard for us to benchmark. So in training, we just pick a small slice. That's this benchmarking region. And that's what our scores essentially mean. Next slide. So the target accuracy that we choose that extremely selectively. So for this, we find a stable region where the training does not drop too fast or is not changing too much. So you don't pick something that's really early in the training curve, not something that's super towards the end, but we find a stable benchmarking region, and all the optimizations that are applied in this benchmarking region theoretically could apply to the entire scale. So if, for example, a result improved by 20% from previous round to this round, it could essentially mean that that same improvement could translate end to end while training this model. Next slide. Right. Okay. So now that we have the background on how MLPerf training actually works, this is our results from 6.0. We had 229 total performance results and no power results in this round. We've also added a new a new result analysis platform thing, and that includes our lowest numerical precision as well as parallelism. I'll talk a little bit more about this in the future slides. Next. These are all of our submitting organizations this time, and we have 4 new submitters. Those are Inventec, NetWeb Technologies, TTA, and Walter. So congratulations to all of our submitters. We have a whole lot of results this time. Thank you. And so in the results, we have 2 separate divisions. We have the closed division and we have the open division. So the closed division, all the results are directly comparable to each other. So they have the same data formats, the same model architecture, the same data loader. In the open division, there's a little bit more novel techniques that can be showcased in that category. But those results are not directly comparable to the closed division results. Also, we have systems that could be available, preview, or RDI. This round, we only have available system submissions. And in the available category under the closed division, we have results from these submitters on cloud and on premise as well. And in the open division, we have 2 results from HPE. Yeah, next slide. So submission trends. One of the big thing I was talking about before is we have 229 performance results in total. That is almost a 1.2x increase compared to last round, which was about 7 months ago. This plot here shows all of our different benchmarks and the number of submissions that we have in each of the rounds. And you'll see here that the light blue bars in the end, that is for this current round. So in general, we've seen that we have more submissions this round for almost every benchmark compared to the previous round. Next. So these last 2 bars are GPT OSS 20B and DeepSeek V3. Those are the new benchmarks that we've introduced in this round. And about 22% of our total submissions were on these 2 new benchmarks. So we're seeing some good adoption for the new benchmarks that we've added this round. Next. Additionally, about 75% of our submissions were on 3 specific models. So they're Llama 2 70B LoRa, Llama 3.1 8B, and GPT OSS 20B. So these 3 models, we're categorizing them as small LLMs. So they're under 100 billion parameters. I think the definition for what is small in the current world is changing a lot. Once upon a time, 100 billion parameters used to be really large as a model network, but in the current world that we're in, these are pretty small proxy models, but they're still a really good model stress test for the entire system. These are easy to benchmark. They're extremely representative architectures. And we're seeing a lot of submissions around these small LLMs because that's what most of our submitters are currently submitting towards. And again, they act as a great proxy towards larger models. Next slide. Yeah. Another thing that we've noticed this time is that we've got a lot more multi-node submissions in this round. This plot here shows the single node submissions versus the multi-node submissions in every round. Compared to about 2 years ago, that was in round v4.0, you can see that the multi-node submissions were only about 33% of the total number of submissions we were getting. But as of this time, more than 50% of our results are multi-node submissions. So in general, we're seeing a lot more multi-node, multi-GPU submissions in MLPerf training. Next. So this is quite a drastic increase. And one of our key takeaways is that multi-node clusters are becoming the standard for MLPerf training benchmarks. And this is what is reflecting the real-world data center deployments as well. Next slide. Right. So this is one of the things I was talking about earlier. We're introducing more transparency in our MLPerf training results. So some of the things like what numerical precision was used in a specific submission, how the distribution was done for parallelism, that kind of information was only available from the code. So it had to be, you have to go through the code, multiple config files to figure out what is being done in every submission. But to make it much more easier to interpret and digest the results, we're trying to increase the disclosure and make this information about the precision used and then the parallelism being used easily accessible to everybody. Next. So the lowest numerical precision, specifically, what this denotes is for each of these different components in an MLPerf training benchmark, like the linear layers, the attention blocks, or the communication section, what is the lowest numerical precision that a submitter is using in those regions, right? That's what they are going to go and disclose with every submission. And the lowest numerical precision essentially means that it doesn't have to be. So if I claim to use FP4 in my linear layers, it doesn't really mean that it's all over, but it just means that at least a fraction of the layers are using this lowest precision. Additionally, to use lower precision during training, you would need to do a lot of additional techniques to ensure your convergence and stability of training. So this round, we've seen techniques like block scaling, healing, and stochastic rounding being used along with the 4-bit numerical precisions in their training recipes. Next. Additionally, parallelism disclosure essentially means that to be able to train on these multi-GPU and multi-node systems, you're distributing your training. And how we're doing the distribution is what we're trying to share with these results. So whether the tensors are being split up, whether different layers of the model are being put onto different accelerators, whether the sequence dimension is being cut up, or how the experts are being separated in our MOE models. All of that information is going to be disclosed. So for example, if a submission has tensor parallelism 4, that means that the tensors are cut 4 ways and split during training. So how you can, next, Laurie. Yeah, so how you can find these results is if you hover over the Tableau table that's shared and click on any of the result, you'll see a tooltip that has additional information about the lowest numerical precision used. And for the parallelism disclosure, you should be able to find that information directly in the GitHub logs. One thing to note is that these two features were added in very close to our submission round, and they were made optional this round. So not all submitters were able to share this information in this round, but it's going to be mandatory going forward. So you're going to have access to all of this information and more going forward in the future rounds. Next slide. Right. So this graph here shows us the lowest numerical precision disclosure for the different benchmarks that we have and the different results. Each of the bars here, there's a lot to take in. So I'll talk a little bit about it, but then I'll leave the rest for everybody here to take in and digest and ask questions afterwards. So some of the things that we see is that the most aggressive precisions, which is NVFP4 and MXFP4, they have been used in the dense models, specifically in the linear layers. So the two lowest aggressive precisions that we've seen this round are these two formats. NVFP4 is NVIDIA's FP4 format, and MXFP4 is an open standardized 4-bit training format. Next. We don't see these 4-bit formats being used in the recommendation or in the MOE models yet. What we think is that for the MOE models with much lower computational density in comparison to the dense models, it adds a lot of additional challenge to reap the actual performance benefits from these lower precision recipes. What we're also seeing is that these precision recipes are constantly evolving, constantly changing. They were used a little bit earlier in the previous round as well. And we're hoping to see more such lower precision submissions in the future rounds. And since MLPerf training is measuring the time to train, essentially what it means is all of these submissions that are coming in are all still training to the same accuracy metrics, but using a wide variety of numerical precisions, optimizations, parallelisms, and so on to achieve that. Yeah, next slide. Okay, so now I want to switch to talking a little bit about our benchmark roadmap. MLPerf training was established in 2018, and since then, the benchmarks have changed quite a lot, I would say. So if you look at this plot here, with the benchmark names listed on the left side, you'll see that a lot of our early benchmarks like ResNet, MassCar CNN, BERT, etc., those are not in our benchmark suite right now. The benchmarks that we currently have in the suite are the ones that are highlighted in blue. And if you see the last column here, they tell when they were introduced and how this is what our current suite looks like. And of the benchmarks we have right now as well, two of the benchmarks, which is our DLRM, DCN V2, and the Llama 3.1405B, this is the last round that we are going to have results for these benchmarks. In the future rounds, we're hoping to have more benchmarks that will replace these ones. Essentially, we add up to 4 benchmarks almost every round and drop up to 4 benchmarks in a year, basically. So what this tells us is that the ML training is evolving really, really quickly. And what we're trying to do is striving to keep pace with the industry. Yeah, next slide. So specifically talking about the recommended model, this is the one that we're deprecating going forward. In this plot, you'll see that we're showing the best time to train in every round. And over about the last year, so from the last, from version 5.0 to version 6.0, that is over the last about 2-3 rounds, the best time to train for this benchmark is pretty much stagnated. The reason for this is that the architecture that we're using in this recommender model is a little old, and our hope is that we can refresh it and add more representative recommender models going forward. But at this time, this is the benchmark that we're going to be dropping. Yeah, next slide, Laurie. Right. One of the other benchmarks that I want to talk about specifically is the super large LLMs that we have in our benchmark suite right now. So we have 2 large pre-training benchmarks. Again, the word large here is loose, but we're saying anything that's larger than 200, 300 billion parameters are the large LLMs we have in our suite right now. So we have 2 of them. One of them is the Llama 3.1405B, and the other one that we just introduced this round, that's DeepSeek V3, which is a 671 billion parameter model. So these 2 benchmarks, in total, they get less than they received about less than 20 submissions this round. But the reason for that is the high cost of benchmarking these really large LLMs. Additionally, the trend that we're seeing is that models like Llama 3.1405B, which were dense models, these architectures in the industry are being replaced by MOE architectures. So, for example, the Meta's Llama models that have recently been released after last year, I believe, they have all been sparse architectures. Similarly, DeepSeek, Alibaba, Google, most of their flagship large models are all using MOE right now. And that's what MLPerf is striving to do as well. So we're moving towards more MOE architectures and dropping our dense models. Another thing we see is that even though we've received lesser number of submissions on these benchmarks, the largest scale submissions comes from these really large LLMs. So we received 8K scale submissions on both of these benchmarks this round. And these essentially just represent the real world data center workloads. And thus, these benchmarks tend to receive the larger scale submissions every round. Yeah, so this is, I guess, some of the insights on all of our results. There's a lot more to understand and interpret in our results. But I would say that each result is unique. So please take a look at all the results. And a good way to interpret and understand the results is by comparing them side to side and looking at different submissions in the closed category and understanding how they differ from each other and so on. So at this point, I would like to pass over to Pawan, who will tell us a little bit more about our new benchmarks that we added this round. Thank you.
Thank you, Shreya. Next slide, please. Okay, let's briefly go over the architecture of a sparse MOE LLM models. What generally happens is you have a bunch of tokens coming into the layer, and in a dense, like a traditional dense LLM model, you have all the tokens going to a single layer. In the sparse MOE model, what you have is a lot of small experts, and each token is routed only to a small subset of the experts that you have in this layer. What ends up happening is you improve the compute efficiency because you're only using a smaller number of flops for each token. And it helps you scale your models better as well because you can, the total compute is separated from the total number of parameters, and you can get better scaling that way. And we generally also see the models are converging a little bit faster using this type of architecture than a traditional dense model. Because of the number of experts, we can also introduce an additional level of parallelism, which was previously mentioned like expert parallelism, which also comes with its own challenges. For example, each token may not be routed for example, there may be load balancing issues where some experts are getting more tokens than the others. So we have to work around that, and different models have different ways of dealing with it. And then there is also semi-costly all-to-all communication overhead when you're doing this routing mechanism. Just a caveat, some of the models may also have a shared expert, which means like all the tokens may go through the shared expert, and some of the tokens will be routed to the routed experts, as you can see here. Can we go to the next slide, please? So we introduced two new models, as previously mentioned, GPT-OSS 20 billion and DeepSeek V3. Both of these are using the same dataset as the dense models that we had before. They're kind of replacing the same real world applications. It's just the architecture is slightly different. I mean, it's substantially different. Can we go to the next slide, please? So let's compare the two dense and the new sparse models that are equivalent to each other. So when we compare Llama 3.1 8B and GPT-OSS, we can see the activated parameters are actually much lower, even though the total size of GPT-OSS is much higher. This is because while we have 32 experts, only 4 of them are activated for each token. The attention module is also slightly different here because it's using a combination of sliding window attention and group query attention. These kinds of models are generally targeted for single node configuration, so you can train on a GPU node and have it scale very well. Can we go to the next slide, please? In this slide, we are looking at the large-scale LLM models, comparing 405B to DeepSeek V3, which we are seeing as a replacement. Similarly, here we have 256 routed experts, but only 8 of them are activated for each token. DeepSeek also has like one shared expert, and it uses a novel attention model called multi-head latent attention, which helps with reducing the memory footprint per inference. The total number of parameters have increased from Llama 4.5b, but again, the total number of active parameters are like much lower because of the sparse routing and everything. The scale for this, as Sri has mentioned previously, these types of models require multiple nodes to scale in a reasonable amount of time, train in a reasonable amount of time, and that is what we are targeting for this particular workload. Again, this is using the same tokenizer and the training data set as a Llama 4FIB. Next slide, please. DeepSeek also brings some additional new innovations like loss-free load balancing, which helps reduce the amount of imbalance that I mentioned previously when we are routing to different experts. It also has multi-token prediction, which again helps with predicting the next token, reducing the time to predict the next token in inference, which requires to add like a couple of additional layers at the end of the module as well. Yeah, these are the three benchmarks that we have added, and I think this is the last slide from me. So if you have any questions, you can go ahead with that.